Good morning, good afternoon, good evening, wherever you are. I'm the first author of this paper. Please call me Edison. I'm currently the postdoctoral researcher in the HKU. Here, I would like to present this paper, The Power of Bounds, Answering Approximate Earth Movers Distance with Parametric Bounds, which has been accepted in TKDE on July last year. After you read the title, the first thing you may ask is, what is Earth Movers Distance? In fact, Earth Movers Distance is a similarity measure between two objects, for example, images. As shown in this figure, we use the feature vectors Q and P to represent these two images. Earth Movers Distance models that each feature value in Q, for example Q1, Q2, and Q3, can move to or shift its values to the feature values of P. Here, we define the value Cij as a cost for shifting the feature value from Qi to Pj. As an example, suppose that C12 equals to 4, Q1 equals to 5, and P2 equals to 3. Once we shift the value equals to 2 from Q1 to P2, that means F12 equals to 2. The cost is C12 times 2, which is 4 times 2 equals to 8. Earth Movers Distance aims to minimize the cost value for shifting the feature values from Q to P. We can model this Earth Movers Distance as a linear programming problem. The time complexity for evaluating this Earth Movers Distance is OD of the power 3 log D, where D is the dimensionality of the feature vectors. In the following, we will abbreviate Earth Movers Distance as EMD. EMD can be used in a wide range of applications in different communities. For example, computer vision, machine learning, and data mining. The two representative applications are image retrieval and document retrieval. The retrieval system represents each image or document as the feature vector. After that, it utilizes the Earth Movers Distance matrix to measure the similarity between the user's query, image, or document and each object in the database. Lastly, this system returns k objects with the smallest distance values to the users. Here, you may ask, there are some other types of similarity measures or histogram matching methods. Why do we need to use EMD as a matrix? The reason is that, compared with other types of histogram matching techniques or metrics, for example Euclidean distance, EMD is more robust, which provides more accurate results in different computer vision and machine learning tasks. In computer vision community, Rubner mentions that EMD is more robust than histogram matching techniques. In machine learning community, Kushner mentions that the WMD matrix leads to unprecedented low k-nearest neighbor document classification error rates. Here, WMD means Earth Movers Distance, which is the same as EMD. Even though EMD is more robust than other types of similarity measures, it is very time-consuming to compute EMD. Many research studies also complain about the inefficiency issues of EMD. As an example, Tang mentions that the high computational cost of EMD restricts its applicability to datasets of low scales. As another example, Huang mentions that datasets may contain hundreds of thousands or even millions of objects, and EMD similarity drawn on them may take weeks to months to complete on a single machine. To avoid the expensive EMD operation, we aim to provide the fast approximation without losing too much accuracy. Here, we propose the error-bounded EMD problem. Given an error threshold epsilon, we want to return a value r such that the relative error between R and EMD-QP is smaller than this threshold epsilon. One easiest approach is to utilize the lower and upper bound functions L and U respectively of EMD to obtain this R, given that the EMD value or E in this figure must be within L and U. We can choose any value between L and U to add as the correct R, which satisfies EQP R less than or equal to epsilon. As such, we need these lower and upper bound functions for obtaining R. In existing work, many researchers have developed the tight and efficient lower and upper bound functions for EMD, as shown in this table. However, one major drawback for these bound functions is that all these types of bound functions do not take the sparsity and the skewness of the feature vectors into account. For skewness, we mean the feature values of some dimensions may be much higher than other dimensions. This property is common in many famous feature extraction methods in computer vision and machine learning communities. To handle the sparsity and skewness of feature vectors, we propose the skew-based transformation bound functions. The idea is to skew small values to other dimensions and make the sparse feature vectors. For example, lambda non-zero bins in the above figure, where lambda is much smaller than the original dimensionality D. With smaller number of non-zero bins, we can reduce the computational cost of EMD, as we can ignore the bins with zero value. As such, we can reduce the time complexity from O d of the power 3 log d for computing EMD-QP to O lambda of the power 3 log lambda for computing EMD-Q-P'. Based on the triangle inequality, we can obtain these proper parametric lower and upper bounds, which are LB skew and UB skew respectively. Here, we will discuss how to obtain these UBQQ' and UBPP' efficiently. During the skew transform for computing LB skew and UB skew, we can maintain the fast incremental upper bound for UBQQ' and UBPP'. As an example, suppose that we move 0.1 from second dimension to third dimension. We can immediately obtain the upper bound 0.1 times C23 after we further shift 0.1 from first dimension to third dimension. We can use this UB move QP' as UBPP'. Similarly, we can also obtain UB move QQ' for UBQQ'. In order to efficiently obtain the approximate EMD value R for problem 1 in slide 6, based on the lower and upper bound functions, we also propose this approximation framework. This framework composed of two components, which are controller and validator. The controller selects the suitable lower and upper bound functions, including our parametric bound functions, and the validator checks whether this pair of bounds fulfills the validation condition. For example, U over L smaller than or equal to epsilon. Once it fulfills the condition, the controller can use this pair of bound functions for estimating the approximate result R. In Validator, except for only using the simplest validation conditions, U over L smaller than or equal to 1 plus epsilon, we also developed the advanced and better validation condition. In our TKDE paper, we show that this advanced validation condition can still fulfill the EQPR less than or equal to epsilon, even though the gap between L and U is larger. For details, please refer to our TKDE paper. In controller, we propose three methods for selecting the lower and upper bound functions, which are ADA, ADAL, and ADAH. However, these three methods are technically involved. As such, we omit the details here. The interested readers can refer to both our TKD paper and this poster paper for details. In our experiments, we utilize two feature extraction methods. which are based on the division of RGB and LAB color space, to extract histograms in 4 datasets. These features are sparse and skew. Here, ADAH is our best method. Both LBproject, LBIM, UBH, UBG, SIAB, and LBRED are the bound functions from the database community. We directly utilize them as the approximation methods. FEMD and Synchron are the approximation methods from computer vision and machine learning communities. To conduct the experiment, we randomly sample 1,000 pairs for testing. In addition, we use throughput pairs per second and relative error to measure the speed and the accuracy of different methods, respectively. Observe that our method ADAH can normally provide much faster solution with low relative error, for example 0.001 and 0.01, compared with all other methods. To conclude, we developed the effective and efficient parametric lower and upper bound functions for EMD. In addition, we further developed the new approximation framework. In our experiment, we showed that our best method can significantly outperform existing approximation methods with low relative error. In the future, our first goal is to efficiently support other types of similarity measures, for example, kernel functions at the distance. In addition, our second goal is to support some interesting applications based on Earth mover's distance. Finally, I would also like to advertise my research work. Except for EMD, I'm also interested in working on the efficiency issues of other types of similarity functions, including kernel functions, Euclidean distance, inner product, especially for kernel functions. Currently, I still have 2 research papers which are under submission to the conference and journal for this topic, in kernel functions. Hope that these 2 papers can be accepted in these venues. Please refer to my homepage for more details of my research work. I'm also interested in transferring our research work into the real product or system to support important, interesting, and timely applications. We, the team in the University of Hong Kong, HKU, and the University of Macau, UMAC, are also developing the near real-time system for using the kernel density estimation KDE to visualize the distribution of COVID-19 cases in the world, in which we believe this is the first web-based system to support interactive KDE-based visualization queries without using GPU or parallel computation. Please refer to this project page for more details. If you have any questions, please contact me via these 2 email addresses. You can just call me Edison. Thank you.